Hello and welcome back to the attic. A few episodes ago I tested a 40 amp DC solid state relay. I wasn't too happy with it. It had a long turn on of 10 milliseconds. Turn off was pretty quick. And so I just got this 60 amp version. And well, the lower trace right here is the input signal going into the input pins, and that's coming from this little pulse generator. You know, these are like $7 or something. These are kind of nice. You can do set the frequency, set the duty cycle, and quite handy for a lot of testing and, you know, even running things. So that bottom signal is the input, and it's noisy as hell. Why is that? Well, it turns out that the other solid-state relay used basically a photon transmission to charge the gate. So basically you have an LED inside, and that shines upon a little solar panel, and that charges up the gate, and it turns on, and that's what powers everything. But this one is different. This one, that bottom signal, is 45 kilohertz. And so what they actually have is an oscillator on the input, and that transfers over to a diode which rectifies it, and that goes into a capacitor and resistor. So you'll have this ramp up, ramp down, and the solid state relay has a very simple FET driver, and those FET drivers all have a certain hysteresis. They turn on at a certain voltage, they turn off, and so what you're seeing is the capacitor charges up, it turns on. It turns on rather quickly. It's about 0.75 milliseconds. And the discharge, because most things with, you know, like a FET driver will have a high turn on and a lower turn off. So it's about 1.5 milliseconds on the output. So the voltage has to decay a little bit once it's turned off, and then it switches off the FET. But if you notice, the FET is turning on very quickly and turns off very quickly. There is a time delay associated with it, but the actual rise time is quite fast. So yeah, I was kind of shocked when I saw that, because I was expecting well, I was expecting more of the same. You know, a bigger FET with a photodiode, maybe even a little longer delay because of increased gate capacitance. But this thing, let me turn this up to 100%. Okay, we're at 100% right now, and I have let's see, probably about 3 to 4 amps going into it, and it's 0.172. I calculated this before at 5.2 amps, and it came out to be that the FET was 35 milliohms. And that doesn't sound like a lot, but you put 20 amps through that, and you're dissipating a lot of heat. Of course, it's just a FET, so if you took two of these and paralleled them together, that would drop the total heat by 1/4. So that would be really advantageous to do. I don't think any of these things can really handle anywhere near the current they talk about. Generally they use the data sheet, max peak current, doing pulse operations, with the thing being relatively cold. And when these heat up, the on resistance will double. So even if you put two of these together in parallel, you soon have the equivalent heat of just one if you kept it cool enough. But that little bit of an oscillator seems really interesting. So let's crank this up here so you can see it. Yeah, so there's your 45 kilohertz. Pretty interesting. And the only reason you can see that is that to drive this, it's basically a 1K pull-up. So you're seeing the current change from the on to the off cycle. And so the voltage changes slightly on the input. Hey, but pretty neat. So yeah, some of them have driver transformers. And with a driver transformer, you can transmit a lot more power than you can with the photovoltaics. So that's it for today.